Now that we're talking about graphing log functions, it probably won't be a big surprise that we're going to graph them in a very similar way to how we graphed exponential functions, because after all, everything else with logs and exponents is more or less the same, or the flip version, or a very related version of the same processes. So let's just start by getting the general shape of a log graph, the simplest one, the parent graph here, y equals log of x. And we'll just kind of make one of our usual XY charts here. And for reasons that you'll see in a second, I'm actually going to put the y's in first. It'll just be easier to construct it this way. So remember, when we have just log of something, that means log base 10. I'll put that here just so we can see it. And so what we're really saying is to find x, like this is the same as saying x is 10 to the y. And so 10 to the negative 2 is 1/100th. In other words, log base 10 of 1/100th. 10 to the something is 1/100th. That thing is negative 2. And this pattern is just going to continue by powers of 10. You can see this is going to be a little bit funny to graph, but let's see what we can come up with here. Actually, I'm going to move this all just a little bit to the side. We might need some room. Okay. Well, it's going to be hard to graph x equals 1/100th. I'll at least put up some little hash marks for the y's. So when x is, basically right here, y is negative 2. When x is still basically right there, y is negative 1. When x is 1, y is 0. When x is 10, I'm not going to go too far over, and then I'll go sort of as far over as I can here. So a little bit off scale, but we've got the general idea that the graph is going to start over by the y-axis, and look something like this. And just as we had an asymptote when we were doing exponential graphs, we also have an asymptote here, except this time we can see it. It's the y-axis. So I'll just note that here. Asymptote at, sorry, it's the y-axis, but it's x equals 0. Okay. And I think what's important to note here is that really the two main points, if we wanted to graph this without making a whole table, points we would look at are 1, 0 and 10, 1. And if we want to sort of make these more general, this would actually always be 1, 0, even if we had a different base. And this would be base, comma, 1. Why is that? Well, because if we had log base b of b, that's always going to give us 1 regardless of what that is. So these points should look kind of familiar because they're just the flip of what we had when we were graphing exponential graphs. So just as a quick review on that, when we were graphing y equals 2 to the x, we said our main points were that when x was 0, y is 1, and when x was 1, y was 2. In other words, we'd have 0, 1, and 1 comma whatever the base was. Well, look at this. We've got same thing, just backwards. So same general idea. And this is what I mean. Pretty much everything that we do with logs is either the same thing or like the flip version, but very much related to how we did it with exponents. Okay, so let's do one more simple graph over here, and then we'll start on some ones with transformations. So y equals log base 3 of x specifically. And in fact, let's take what we learned here, that we're going to have 2 points. We're going to have 1, 0, and we're going to have base, in this case 3, comma 1. And we could check these points, right? If we put in x log base 3 of 1, so the exponent that turns 3 into 1 is 0. And then log base 3 of 3, the exponent that turns 3 into 3 is 1. Okay, so these points work. So I'll put them in here. we have when x is 1, y is 0. When x is 3, y is 1. We know that we're always going to have that asymptote on the y-axis at x equals 0. Draw that in there. And so we know that this graph is going to start along that axis, go up, kind of curve down that way. And that would be our graph of y equals log base 3 of x. So let's try this now with some graphs that are log graphs, but also have transformations. And I think you know what to expect by now, that we're going to treat these transformations the same way that we've treated them in every other kind of graph that we've done. So here, set that equal to 0, x equals 3. So in other words, that goes 3 to the right. And we know this means the graph goes 1 up. So just as I did when we were graphing exponential functions, I'm going to just take care of these right from the beginning. And I'm going to sort of draw my own axes in here and say, okay, there's that one. There's that one. So I'm going to say, great, I've dealt with the horizontal and vertical transformations. And so now all I really need to think of is y equals log base 2 of x. And that's going to be relative to these new axes in blue. And if we look at our hint from the last page, we know the 2 points now that we're going to be interested in, 1, 0 and b, 1. So let's do that. We've got our 2 points here, 1, 0, and base, the base is 2, 1. So I can just put those points in, again, relative to this new axis that I drew. So 1, 0, so that's 1 over and then none up, and then 2 over, then 1 up. And I know that this is going to be my asymptote. It's now at x equals 3 because we went 3 to the right. And so it's going to start along that asymptote, curve up like that. So let's apply that same set of ideas one more time here. All right, y equals, so we've got one thing that's different, which is just this. So we'll make sure we deal with that when the time comes. But otherwise, we know how to start by dealing with our horizontal shift and vertical shift. So that's going to be left 1, and this is going to be down 4. And as I did before, I will put in my new axes. And we'll try to do a good job of drawing those. So there's, okay, that's pretty good. And then I can move that a little bit. Okay, close enough. And so with that, I've dealt with the horizontal and vertical transformations. And all that I really have to deal with now is y equals 3 log base 5 of x. And again, we know the points that we want. We want 1, 0, and we want b, 1. So in this case, the base is 5. Except not so fast because there's this 3 here, right? We know that this is going to stretch everything vertically by a factor of 3. So that 0 is going to become 0 times 3. That doesn't change anything. But this 1 is going to become 1 times 3. So that's actually going to be 3. So it's the one little trick there. You could still think of it just in terms of putting in the x value that's going to make this work out easily. So if we do 3 log base 5 of 1, this part's going to be 0, multiply that by 3. 3 log base 5 of 5, this part's going to be 1, multiply that by 3 is 3. So either way, you end up with these 2 points relative to our new axes. So let's put those in. So we've got when x is over 1, y is 0. And then when x is over 5, so let me put in, so that's, remember, this is our starting point. So this is like 1, 2, 3, 4, 5. Then y is up by 3. So it'll be there. It'll be up by 1, 2, 3. Start along the asymptote. That was kind of an ugly start. Start along the asymptote. Close enough. Make that a nice big dot and it'll look perfect. And then we've got this asymptote here at x equals -1 because that was our horizontal shift. Now, you could always graph these by, if we go back to this original function, and I'll do this in another color. So I'll write this again down here. The big thing here, and there's a couple different ways to do this, but the big thing is if we want to get a couple points, we want log base 5 of a couple of easy things. We want log base 5 of 1 because that's going to be 0. And we want log base 5 of 5 because that's going to be 1. So another way you could do this is you could say, all right, we want them. Okay, we want this to equal 1. So we want x to be equal to 0. There we go. So we want x to be equal to 0. All right, when x is 0, x 0 plus 1 is 1. Log base 5 of 1. So this is 0. 3 times 0 is 0. Minus 4 is -4. So we end up with a point 0, -4. Well, we have that point. We just got it in a different way. We also want to do log base 5 of 5. Okay, for this to be 5, x needs to be 4. So log base 5 of 4 plus 1. Log base 5 of 5 is 1. 1 times 3 is 3. 3 minus 4 is -1. And okay, we have that point too. So of course we end up with the same points. What unifies those two ways of thinking about how we're graphing this is that we need to take log base whatever of 1, and we need to take log base whatever of that base. That's the important part. We need log base whatever of 1, and we need log base whatever of that base. Those are the two key points. Because if we put in any other numbers, if we put in, hey, what if we do x equals 7, and we have log base 5 of 8, that's some weird decimal that we can only do with a calculator, and it's just not helpful in terms of graphing these by hand. Okay, last thing on log graphs. And I'll go back to the very beginning here, and we'll go to this one, log base 3 of x. We know at this point that log functions and exponent functions are inverses of each other. And we also know what inverse functions should look like when you graph them. They should be reflections across the line y equals x. So let's graph the corresponding exponential function on this same graph and just make sure that it works out that way. So if we have y equals log base 3 of x, the corresponding exponential function would be y equals 3 to the x. When I say corresponding, basically I mean the one that should be its inverse. Same base, right? Base 3 in both cases. And going back to how we graphed exponential functions, we know that we'd have 0, 1. Remember, it's these same points that we were just talking about, just flipped around because we're working with them now in an exponential way instead of a logarithmic way. And 1, 3. Okay, so let's graph these 2 points. When x is 0, y is 1. And when x is 1, y is 3. And remember, for exponential graphs, we have that horizontal asymptote on the x-axis. So we end up with something like that. And I'll also throw in here do my best to be accurate with it. The line y equals x. It should be pretty good. And I think we can see pretty clearly here, even for just a sketch, this is pretty good in terms of showing these graphs and these points being reflected across that line y equals x. And just as they should be for two functions that we know are inverses of each other, the graph certainly lines up that way as well.